happens when you square a negative? Becomes positive, right? But don't forget, we still have to square the number, right? So you can even think of it like this. I have negative x times negative x. The negative times a negative is a positive, and I'm left with a positive x squared. So we still have to square the x, but the negative goes away. Let's go to the one underneath. When I have negative x, quantity cubed. What happens when you cube a negative? Stays negative. Well, we still have to cube the x, don't we? So again, you could write negative x times negative x times negative x. The negative times a negative times a negative is a negative. X times x times x is x cubed. So it's important to note, when we square it, the negative goes away. When we cube it, the negative stays, but I don't need parentheses anymore. So to me, it's simpler, isn't it? What if, and I know this is not written on our paper, but what if it was negative x to any even power? So what if this was not a 2, but a 4 or a 6 or an 8? What happens to the negative? Goes away. The power stays there, but the negative goes away. Or what if I had negative x to any odd power? What happens to the negative? It stays. And we still need to raise that x to the odd power. This is kind of just in general, kind of writing it generically, yeah? Also, what about the one on the top right? 1 over negative x. Again, if I'm asking you to simplify, we're saying, like, let's get rid of parentheses or just combine like terms. First of all, do I need parentheses down there? I don't think so, right? So one thing we could do is write it as 1 over negative x. Like, you don't need the parentheses. It's not like we were squaring it or multiplying it by anything. So maybe I should ask a different question. Is there a nicer way to write this or a different way to write this? It's kind of an open-ended question because I think there's a lot of answers here. Michael?
Negative x to the negative.
So we could use negative exponents. Absolutely. Some people will argue that negative exponents make it look now more complicated, but you're right. That would be a way to rewrite it. I'm actually just going to take what you started with. Would you agree that the one on top is positive? And then on bottom, I have a negative. So a positive divided by a negative is a negative, but I still want to divide the 1 by x. Did I really do anything different? No. All I did was move the negative out in front. And it means the same thing, right? When we talk about a fraction with a negative, negative 1 divided by 3 is the same as 1 divided by negative 3, which is the same as negative 1/3. Agreed? That's what I just did there. 1 divided by negative x is the same as negative 1 divided by x. I'm doing this for a reason. You know, I like to save us time later when we're in the meat of a problem. This is going to help us later so we're not like, time out. We already have the timeout done. Let's take a look at this last one. The absolute value of negative x. Say it again.
Makes it positive.
Makes it positive. Makes what positive? It gets rid of the negative. Does the absolute value go away? Tricky. This is and this is why I'm asking, because I think this is one of the hardest ones up here. I think it is the hardest one up here. Some of you will say, hey, like for example, I'm running out of space here. The absolute value of negative 3 is 3. Like the absolute values go away with the negative, right? What's the absolute value of 5? Just 5. That's okay. That's okay. I know. We started thinking, you just change the sign, right? You know, when there is no negative in there, we don't really need it. So the tricky thing here is that when we look at it numerically, we say, oh, the absolute values are going to take away the negative and they also disappear. So it would be very easy for us to just write down x. However, that's not correct. And this is what's tricky about leaving it as a variable. What if I asked you to go plug in a -2? What if x equals -2. If you put a -2 in here, now it's the opposite of -2, which is 2. And what's the absolute value of 2? 2. But what did we say x was? -2. And so now we have a 2 on this side, but it doesn't work, does it? The tricky thing here, and I'm going to write it out a little bit differently. Now, without a number in there, we actually have to leave the absolute values, and I'll explain why. Kind of like what I did over here. Remember how I wrote it out as like a -1 times something? Here, it's really like, whoops. It's really like writing, those are my absolute value bars. It's really like saying the absolute value of -1 times x. What's the absolute value of -1? 1. That we can kind of slide out and say, yeah, we know the absolute value of -1 is 1, but then we still need to take the absolute value of x. That's a tricky one. And without spending 20 minutes on it, and we can. Let's move on, but I would love to, if you're still sitting there going, I just don't get it. I just don't see what you're saying. Let's talk about it. Let's, after class, just wait for 3 minutes. I won't keep you for 20, but let's talk about it, and I'll show you on a graphing calculator what I mean, okay? So here's the big takeaway here. I'll box this one in because I've made a huge mess of this slide, and I apologize. But when you have the absolute value of -x, we can just replace that with just the absolute value of x. Okay. All right. Wow, that is a huge mess. But I apologize. Let's move on. Get rid of the mess. So let's talk about what this really means today. What I'm talking about with symmetry and this idea of an even and an odd function. We know even and odd numbers, right? But what does it mean when we're talking about a function? When we talk about it graphically, we're going to do graphically and algebraically today. Graphically, even functions are symmetric over the y-axis. And we know symmetric, I could also say reflections over, right? Symmetric or reflections. And I'll explain that with some graphs. I'll use 2 graphs and maybe we'll come up with a non-example here. Symmetric over the y-axis means whatever you see on the right side, you're going to see a mirror image of on the left side. A perfect example of that would be our parent graph of y equals x squared. Mine's not well drawn. You can use your imagination on that. But look at that. That axis of symmetry is the y-axis. Cuts it right down the middle. Let's draw another graph. This one may not be a parent function. What if I drew something like, like the letter M, whether you put arrows on the bottom or not? This is an even function, right? Because look at that axis of symmetry. That middle line is the y-axis. Now I'm going to give you a non-example. This one is not an even function. It's still that same M I drew. This is not an even function. Does it have symmetry? Yes. Where is that line of symmetry? Well, it's not on the y-axis. So when we talk about the symmetry today, I'm not just talking about graphs that have any symmetry. I'm talking about specific. In this case, it's symmetric over the y-axis. This one is symmetric. It's just not on the y-axis. Okay, so I want to make sure that kind of clarified that definition a little bit. Well, it would seem like it would make sense that if even functions are symmetric over the y-axis, then odd functions should be symmetric over the x-axis. We only wish. Let me explain. Don't draw this. Because if something was symmetric over the x-axis, is that a function? No. So we want to be very careful. We don't jump and just say, oh, well, even means this, so odd means like the other, the opposite. That's not the case. So odd functions, and I'll write it down a couple of ways, and then I'll show you graphically. Odd functions are what we say are symmetric over the origin. I'm going to explain what that means. Symmetric over the origin means it has been rotated about or around the origin, 180 degrees. Some of you might think, oh my gosh, I did not do so well with rotations in geometry. So don't let that freak you out if that's going to bother you, because I don't like to think of it that way. The other way we can think of it is that it has been flipped, or maybe I should say reflected over both axes. I'll explain with a graph. Let's get those written down. I know it's a lot, so I'm going to pause. So odd functions, we can say, have been reflected over both axes, the x then the y, or the y then the x, and it doesn't really matter either way. While you're still writing, I'm going to go ahead and just get myself some example graphs here. I'm going to start in the first quadrant with like half of a parabola. If this graph was even, we would flip it like this, wouldn't we? If the graph was even, we would first flip it over the y-axis. Odd functions, we say we're going to flip over both. So temporarily, I flipped it over the y, but now I'm going to take this and reflect it over the x. And then I'll erase my little dashed lines there because they were just helping me come up with my graph. This is an odd function because this image that was in the first quadrant flipped over the y, and then I flipped it down over the x. That's what I mean when I say it's been reflected over both axes. I didn't leave that first image there. I just used it to help me get here. If we kind of come back up to here where it says it's been rotated about the origin, it means if I take this point here and I go, whoop, it's going to land down here, 180 degrees. If I take this point, I can rotate. I mean, my picture's not perfect, but I can rotate it. I don't think you're going to want to think of it as a rotation, but that's another way to explain it. Okay. Erase, erase, erase. Okay. Let's come up with another. That's a parent graph. To me, that's like the graph of y equals x cubed, or maybe part of a tangent graph. Okay. But maybe let's think about one that's not as comfortable for us. Maybe I do something like this. For my first half, I'm just drawing half of the graph. If I want to turn this into an odd graph, the first thing I'm going to do is just very lightly with my pencil make it an even graph. There's that M that I talked about earlier. And then I want to flip this dashed graph over the x-axis, and so it's going to come down and then go up. And then I'll take my pencil and just erase that little helper graph that I used. If you want to leave it there for your own purposes in your notes, that's fine. But I wanted to erase it just so we could really focus on what this graph looks like. That would be considered an odd graph because whatever I see on the left side was flipped, then flipped. So two reflections. Okay. All right. That's what odd graphs are. So even and odd. You would think they'd be a little more connected, you know, but that's okay. All right. So let's take a look at this question. It says, find the coordinate of one other point on the graph of the function, if possible, given that the function in the first case is even. Now, I'm not going to draw a really elaborate graph here. I'm just going to give myself a cute little set of axes here. And they're telling us that my graph goes through the point 2, 5. I don't even need to like put little tick marks. I could have just put it in the first quadrant. Whatever you need that. I know that this graph contains the point 2, 5. They're saying, hey, then tell me one other point that this graph goes through if we know it's an even graph. I don't need the shape of the graph, but an even function says whatever's on the right will be on the left, or whatever's on the left will also be on the right. Flip that point over. You did so much of this in geometry, right? So if we're going to just flip this to the other side, what are the coordinates of my new point? -2, 5. And maybe I should have written it a little bit bigger. -2, 5. That's our answer. So when we know 2, 5 is on the graph and we know it's even, then we already know then that -2, 5 is on the graph. What did not change about the point? The y-coordinate, right? Because I didn't change the height of the point. I just changed the side-to-side coordinate, the x-coordinate. Let's talk about this next one. They're telling us that this is going to be an odd, it's a completely different graph. Doesn't even matter what the graph looks like. They're telling me it's odd, and they're telling me that I have the point -3, 4. I didn't even put the tick marks because I want to prove we don't need the tick marks. You can put them there if you want. I want one other point on this graph. What am I going to do? Go ahead, Michael. Perfect. We're going to flip this point twice, and then we'll write the answer. But we're going to flip this point across to the other side first to give me 3, 4. That makes it even. To make it odd, we're then going to flip that point down, which would be still a +3. But then when I flip it down, the y changes to a -4. So I didn't draw any graph. I just said, look, I want to reflect the point 2 times, which Michael said, you're just going to change both sides. We started with a -3. Now we have a +3. We started with a +4, and now we have a -4. So odd functions, you change the sign of both coordinates. And that's going to lead us to being able to write down something a little more generically about even and odd functions. Okay? So let's take this concept here, and now let's start talking about how we can like algebraically talk about even and odd. So an even function containing the generic point AB will also contain the point -AB. Right? So this is just taking the numbers out and just putting some random, they're not random, but you know what I mean, some letters in there. If it's an even function, you change the x, but it does not change the y. Let's write that a little bit differently. In general, for even functions, when you plug a -x into the function, it will still spit out the exact same y. That's not, I said something different than what I wrote. I wrote f of -x equals f of +x. What does f of x mean in mathematics? What does it represent?
Y.
It means y. So we're saying, you don't have to write this down unless you want to. The y value at -x is the same as the y value at +x. That's what that's saying. Looks pretty formal, doesn't it? Hey, Adam, you looking for some packets?
Right here.
Right there, one of each. Awesome. But that's what it's saying, that the y value at a -x is exactly the same as the y value at the +x. It's just a really fancy way of writing that, isn't it? Let's do the same thing with odd functions. Taking what we just did on the previous slide, Michael said, well, you change both signs if it's odd. So if I have the point A, B, my next point will be -A, -B. Both signs change. How can we write that maybe a little bit more maturely, or more like in terms of mature mathematics? If I plug in a -x, what happens to the y? What happens to the y coordinate? Doesn't it also change signs? So if I plug in a -x, I'm going to get the opposite of the original y. This is saying, I'm not going to write it, but this is saying the y value at -x will equal the opposite of the y value at +x. It's saying the same thing. It's fancier notation. And not fancier because we can be, but fancier because sometimes we need to be. We need to be a little more concise or specific with our language. Okay. All right. Are we ready to flip our notes? All right. We're going to skip, and that's okay, but we're going to skip this slide right here and come back to it on Monday. But I promise we're going to come back to it. I have time set aside for that. But what I want to finish with, and we may only do one of these, and that's okay. I want to finish with this. Algebraically, so we're not going to graph it. We're not going to get a calculator out. We're going to look at algebraically determining if a function is even or odd. We're going to use the two statements we just wrote down in those gray boxes. Okay, so, and we can check it. I don't think we'll have time today, but we can check it on a calculator on Monday. Here's f of x. F of x equals x squared minus 3x to the fourth plus 2. I want to know if that's even or odd, or maybe neither. Not all graphs have any symmetry at all. First thing we want to do, we want to find f of negative x. And here's why. And I know you flipped your notes. I'm going to switch back for a second. Because I want to know if f of negative x gives me f of x, oh, I know it's even. If f of negative x gives me the opposite of f of x, then I know it's odd. So that's what we should do first. Let's find f of negative x. How do I find f of 2? Or f of 0? Or f of 18? You just replace x with that number. So if they want me to find f of negative x, I'm going to replace x with negative x. And maybe I should do that here, right? F of negative x. Let's just go plug a negative x in for every single x. And some of you are going, oh, wait, what are we doing? Hang tight. So on the left-hand side, I'm going to leave that alone. But on the right-hand side, let's clean it up. We did this work at the beginning of class today. Remember how we said negative x squared simplifies to just be x squared? We already did that. You know how I like to do that ahead of time. Here we have minus 3 times. Do you remember how we said also at the beginning of class today? Negative x raised to an even power will be x to that even power. And then we still have our plus 2. I just simplified those negatives. I'm sorry, I'm standing right in your way. I just simplified these things here in pink. Does this look familiar? It's what we started with. Isn't this equal to f of x? Isn't it? Oh, it is. So we just found that f of negative x equals the original function f of x. What does that tell me? You might have to flip your notes back. What does it tell me if f of negative x equals f of x? It means it's even, and I'll go back. F of negative x gave us the exact original function f of x. Okay, I am going to finish this lesson on Monday in class online. So if you encounter something on worksheet 7 and you're like, I don't know, just hold off. Okay, just hold off. Enjoy your 3-day weekend. I will see everyone online on Monday. Okay.